In this lecture, we'll be addressing a very important and a very subtle topic, okay, of thermodynamic equilibrium. In fact, the preamble to this lecture is the previous lecture on features of system, a macroscopic system that is not in thermodynamic equilibrium. Okay, so we were trying to, in that lecture, we talked about certain driving forces which give rise to fluxes. Okay, so these fluxes and driving forces are indicative of systems that are not in thermodynamic equilibrium. So here we will elaborate on what exactly do we mean by thermodynamic equilibrium. So in the past, we've introduced two kinds of system: open system and closed system. There is also another system. It looks a bit artificial, but it's just a system with which we can discuss thermodynamic equilibrium very well. So this is called isolated system. All right. So these are systems that cannot exchange both either matter or neither matter nor energy can be exchanged with the surrounding. Okay, it's completely isolated. Okay, so that's so it's different from closed and open system. So this is called an isolated system. So this is a definition which I've taken from this book, which I mentioned. Okay, it's a thermodynamic equilibrium we are talking about a system, thermodynamic system, wherein none of the thermodynamic properties are changing with time at a measurable rate. Okay, so there is a certain amount of empiricism. Okay, that is when we are trying to measure something, and when the thermodynamic properties like temperature, pressure, total energy of the system are invariant with time. Okay, at a measurable rate. Okay, we cannot measure these changes. Then we say that this system is under thermodynamic equilibrium. All right. So we are talking about an isolated system, right? So we are not talking about, obviously this definition excludes because we are talking about isolated system, this definition excludes existence of steady state processes. In steady state processes, there is a difference, that the driving force between surrounding and the system under consideration, which gives rise to fluxes, which may, in that case also, the thermodynamic properties can be invariant with time. But these are all not isolated systems. These are steady state processes, and we are not talking about such systems. So here we are specifically talking about an isolated system, and the thermodynamic properties are not changing with time. So there are other features which are observed in nature. There are reasons for this. We'll see in the next couple of next couple of slides. Equilibrium is unique. Okay, so wherever you start, all right, irrespective of where you start, this equilibrium state can be reached. Okay, that's what is seen empirically, and the way you reach it is via what is called an irreversible path. Okay, irrespective of how you start the system, you are able to reach a particular equilibrium state. Okay, so that is one of the features of an equilibrium state. There's a unique state available. There is a reason for this also. The uniqueness of an equilibrium state for a simple system like an ideal gas, okay, so can be rationalized because all these simple systems obey what is called an equation of state. Okay, so you know the ideal gas equation, that's an equation of state. So in this, the fundamental thermodynamic variable, there's a function which is called the equation of state. In the next chapter or so, we will elaborately discuss this equation of state, but you have an idea of equation of state at least for ideal gas systems. Okay, so this is one of the reasons why the equilibrium states are unique. having said all these things, this is not very trivial. Okay, for simple systems like an ideal gas, okay, uh, uh, it looks trivial, but in practice, this is how to establish whether a system is under equilibrium. Okay, it's an equilibrium, and what are the relevant thermodynamic variables that characterize a system in equilibrium is not at all trivial. Okay, so that's where, see, one of the main challenges with thermodynamics is you can learn many things. Okay, how do you implement in your lab? Okay, when you really troubleshoot, when you go to join an industry or go to a lab, how do you translate what you have learned to real system is not trivial. Okay, so uh, for example, when most of the solids, most of the materials are uh, there is a particular way we process these materials. For example, in steel or glass. Okay, so there is a certain thermomechanical treatment which you employ to change its fracture properties or toughen the steel and so on. All these processing which you employ on the material introduces certain strains. Okay, so we really do not know whether the system is actually under equilibrium, a glass. Okay, so the system, when you are talking about a measurable rate, it is sort of a limitation of your the way you measure. Okay, so if you observe it for few seconds or few minutes or even few hours, things may not appear to change. But if you leave it for a long period of time, things go and change. For example, if you go to certain old forts, you may see, or even churches and so on. Okay, so you may see certain glass is typically transparent, but it would have crystallized. Okay, so because especially in South India where the temperature is higher, which accelerates the rates. Okay, so the glass would have crystallized, and it's no longer, the glass is no longer transparent. Okay, there are some spots which are not only translucent but can be opaque. Okay, these are all indicative of the feature of the glass, that glass is not in equilibrium state. Same thing with steel also. Okay, so these are not equilibrium states. These all have internal states, internal strains and so on. Okay, so this reproducibility is very much dependent on whether you can control the relevant thermodynamic variables. Okay, so that what are the relevant thermodynamic variables, that is not at all straightforward, especially in these systems, because there are some internal strain states which you cannot control so easily control. Same thing with heterogeneous systems. For example, if you have a very porous solid which has some adsorbed gases, that is, there are some gases that stick to the surface of the pores. Okay, so it's not at all clear what are the relevant thermodynamic variables which you have some control, which helps you reproduce those states. Okay, so for thankfully these are not what we are going to be discussing in this introductory lecture. But if you go and take a class in material science or in chemical engineering, these kinds of systems will be addressed, but you should be aware of these complexities. Okay, we'll be looking at much simpler systems that has certain pedagogical utility. These simpler systems have certain pedagogical utility. For example, the simplest system, okay, so we'll be looking at is ideal gas. Okay, so things are ideal at low pressure and high temperature, right? So you've been exposed to this from your kindergarten, I suppose. You know the equation of state for an ideal gas system. So PV is equal to nRT. So what exactly do we mean? Okay, so when you change one of all these things are not independent variables. Only few things can be changed independently. When you change one of them, the other thing changes by itself. Okay, so for example, if you change the temperature and volume, okay, so the number of moles is also changed and so on. Okay, so you have a sense for equation of state, but we will look at this in much greater detail. So just because I introduced this term equation of state, I just wanted to tell you that you already know a simple equation of state. So there are only few independent variables in this system. This is determined by what is called the Gibbs phase rule, which you will hear in the as you progress along in this course. The number of independent variables are also called degree of freedom. Okay, so you must be aware of these terms, because sometimes when you read these reference books which I discussed, okay, so these things are discussed, so you shouldn't suddenly get surprised when they use these terms. These are not such a deep concept, but at least you should be aware of these terms. All right, so to emphasize again, at equilibrium, there are no driving forces for changes within the system. So what do you mean by that? For example, when you're talking about a thermal equilibrium. So to begin with, this system is not, this is an isolated system. There is no mass exchange, there's no energy exchange. Okay, so this is a system for at least, let us think in this manner, this at least a closed system, okay? That's what we can say. So here we are talking about a closed system, because there has to be an exchange of energy, right? So the ambient temperature is, let's say, 32 degrees centigrade. So when we start the system, the different parts of the system are at different temperatures, all right? So when the thermal equilibrium is established, the temperature is uniform. There is no variation in temperature. And this temperature is 32, which is the temperature of the outside environment. Okay, this is a closed system which can exchange energy. There's an energy exchange between the surrounding and the system. So thermal equilibrium. So when you talk about thermodynamic equilibrium, that is much more than thermal equilibrium. Okay, so thermal equilibrium is one aspect of thermodynamic equilibrium. We'll see the other features. When you talk about mechanical equilibrium, we are talking about pressure. Pressure is uniform inside the system and does not vary with time. Okay, so that is indicative of mechanical equilibrium. That the temperature does not vary. Once the equilibrium is established, temperature does not change. Okay, that uniform temperature and time invariant temperature is indicative of thermal equilibrium. Uniform pressure and time invariant pressure is indicative of mechanical equilibrium. Chemical equilibrium. Okay, so the chemical composition is uniform within the system and it does not change with time. Okay, so that is called chemical equilibrium. There is something called phase equilibrium. We will talk about this at later as you progress along in this course. So here it has more than one phase. Okay, so for example, there can be two phases. There can be a liquid and a gas. Equilibrium between gas is one phase, and there is a uniform property thermodynamic. There's a uniformity in thermodynamic property, and it doesn't change with time. Also in the liquid and a gas. Okay, so this need not be just one component system. The liquid can be a mixture, and the gas can also be a mixture. But the chemical composition of both the liquid and the vapor in contact with the liquid does not change. Okay, so there's something called phase equilibrium, but we'll talk about this in much later as we progress along this course. Okay, so what you should understand is, when we say some system is under thermodynamic equilibrium, all these things have to be obeyed. There should be thermal equilibrium, mechanical equilibrium, chemical equilibrium, and also phase equilibrium. When all these things are obeyed, that's what you mean by a system is under thermodynamic equilibrium. So we will. Okay, so we have to also understand, okay, so certain complexities associated with definition of thermodynamic equilibrium. So you might have heard something about a stable equilibrium. So what are we talking about? So we are talking about a ball here. So when I move the ball here little bit, that is, if there's a fluctuation that makes it displaces the ball away from its equilibrium, what will happen? There is a restoring force which gets the ball back to equilibrium. Okay, so this equilibrium state is stable, when you say it's a stable equilibrium state, this state is resistant against towards fluctuation. Okay, it comes back. There's a restoring force that brings it back to the same position. That's what you mean by a unique stable equilibrium. Okay, so even this is in a simple context of a mechanical system, a ball in this kind of a shape, but this you can also translate this analogy to thermodynamic system. Okay, the thermodynamic system can fluctuate. If there are some fluctuation, suddenly the temperature increases, okay, or the pressure increases, the equilibrium does not move away. It is the equilibrium state is stable. Okay, there is a unique equilibrium state that is stable against fluctuation. So this is not always true. Okay, in the stable states are not always present. Sometimes, okay, there can be unstable states and neutral equilibrium states. What do you mean by unstable states? Again, I'm using a simple mechanical analogy. So if this ball is in this kind of position, okay, at this position, it is there is an equilibrium. Okay. However, when there is even a small fluctuation, this is unstable. It will go to a different position. Okay, so just contrast this system against this system. This system is stable against fluctuation, resists fluctuation, whereas this system, this is an equilibrium position. Okay. However, this system is not stable, resistant against fluctuation. This is called neutral equilibrium. This is stable, this is unstable, this is neutral equilibrium. That is, when there is a fluctuation, this attains a new equilibrium state that has the same energy, all right, as this particular state. So you have to be aware. So most in thermodynamics, okay, while these things are possible in simple mechanical systems, in thermodynamics, typically you don't see unstable or neutral equilibrium state. There are a lot of fundamental microscopic reasons why this is so, but most of the time, at least for simple systems, what you observe is a stable equilibrium that is resistant against fluctuation. However, what you do see, even for a simple system, is what are called metastable states. All right, so we will understand what's a metastable state. For example, to give you a concrete example, when you have, let's say, a closed system, you have hydrogen and oxygen. All right. So actually, the hydrogen and oxygen in most concentration, most partial pressures, it's a combustible mixture. Between 4 to 96%, it's a combustible mixture. The stable state is actually water. It is not hydrogen and oxygen. However, due to certain reasons, the reasons I'm talking about is when H2 reacts with O2, this reaction involves an activation barrier. Okay, so this activation barrier is not a small amount. There is a reasonable, significant activation barrier. So in most cases, hydrogen and oxygen can be kept in a metastable equilibrium. So that is, the energy of this metastable state is higher than the stable state. Higher than this stable state. So this is the state wherein hydrogen and oxygen are present, but to go to the most stable state, which is water, it has to go through this activated state. Because of the presence of this activated state is like an internal constraint. This prevents the transformation of hydrogen, oxygen to water. Okay, so these states are called metastable state. These do occur in most of the thermodynamic systems. Many of the thermodynamic systems, metastable states are not uncommon. In fact, when you talk about diamond and graphite, diamond is a metastable state. Okay, graphite is the more stable state. It is very interesting to, if you look at the energetics, graphite is more there are ways to quantify the energy of graphite and diamond. Graphite is more stable compared to diamond. Diamond is a metastable state. it after a long period of time, okay, it might get transferred to the more stable state graphite. Okay, if somebody asks you that why is that you're not able to give me a diamond ring, okay, you can tell them that, okay, I can give you a graphite ring, okay, so that is from lead pencil you can get, and say because the diamond is metastable. All right. Okay, so typically what we are talking about in this course will be transformation of very simple systems. Okay, so typically, again, we are coming back to piston here because you have elaborated why we talk about pistons very often. So the transformation we'll be addressing will be calibrated by certain thermodynamic properties. It can be like temperature and pressure. And when we want to go from state one, which is indicated by certain temperature, pressure, and so on, to another state, which is again has a different thermodynamic variables, we would be discussing certain path. Okay, this path is a construct. Okay, this doesn't happen in realistically, but it's a construct that facilitates analysis, thermodynamic analysis. What is this path? When we say, let's say this path is, let's say state one is, let's say this one, and state two is this position. When we move from, how do we move from here to here? This is, we do it very, very slowly. These are called, what is called quasi-static. What do you mean by quasi? Quasi means almost, okay, almost static, okay. So you, okay, so you move this very, very slowly, as if while during this movement, the system is at equilibrium. Okay, that is what, there's a uniformity in thermodynamic variables in the entire system. If you move very fast, okay, so this is not a quasi-static process. The thermodynamic variables will not be the same. For example, when you move very fast, the pressure can be greater here compared to here. Okay, there can be flow and so on. There is a non-uniformity of thermodynamic variables inside the system. This is what happens in reality. Okay, so if you ask the question, how long will it take for you to transfer from this state to this state using a quasi-static process? It will take infinite time, right? Because you do it so slowly, there are only infinitesimal change, so you take infinite change. Okay, so, but the advantage of considering such a path for analysis is that I can describe each state using equilibrium relationship. Okay, so even though such a path does not exist in reality, this processes can be analyzed within a certain framework. Okay, born out of equilibrium thermodynamics. That's why you use these quasi-static or quasi-equilibrium states. All right. So this is an important, a clever way of dealing with real transformation. We'll see the power of this. Of understanding and analyzing such transformation. It gives you some bounds in efficiency and so on. For example, typically we will be looking at, for example, this is the PV diagram. Okay, so pressure is on the y-axis, volume is on the x-axis. So the initial state has this much volume, the final state has much lesser volume, and you will be going from this state to this state using an quasi-static process. Right? So there are many processes we'll be looking at. For example, something called isothermal process. Iso means same. Okay, isothermal process means process transformations, whereas temperature is the same. All right. Isobaric process. Okay, we are not talking about a person who's stuck in the same bar. Okay, that's not what we are talking about here. So isobaric means the pressure is same throughout the transformation. Okay, isochoric process or isometric process, volume is the same. But the most important transformation, which we'll be looking at, this is in fact the climax of the course, okay, will be analysis of cyclic processes. Okay, we'll be looking at what is called a Carnot cycle. You remember this thing which I told in some previous lecture? The linear cyclic motion of a piston gives rise to rotatory motion, right, of a wheel. Right? So this we'll be looking at a particular kind of a cycle, Carnot cycle, which is very, very important in this energy conversion. What kind of an energy conversion? How much work can be obtained when you supply certain amount of heat? Okay, how much of the heat can be converted to work? Okay, so that's in fact the climax of the course, and then we look at other details. Okay, so there are so these are different kinds: isothermal, isobaric, isochoric. But the pinnacle of all these processes are certain kinds of cyclical processes, which we will look at as we in the next after few lectures. Okay, so with that, I will stop this lecture on thermodynamic equilibrium.